Rounded nose. The rounded nose is the most common design found on subsonic commercial and general aviation aircraft, including airliners such as the Boeing 737, Airbus A320, and virtually every light aircraft flying today. Its blunt, curved profile houses the weather radar antenna behind a composite radome at the very tip. At subsonic speeds, the rounded shape manages airflow efficiently without excessive drag, and its large internal volume makes it ideal for containing the radar electronics, sensors, and wiring that modern aircraft require forward of the cockpit. The smooth curve also distributes aerodynamic loads evenly around the nose section. On twin-engine turboprops such as the Beechcraft King Air, the rounded nose typically contains baggage space rather than radar, making use of volume that would otherwise be wasted. Pointed nose. The pointed or conical nose is found on high-performance military jets and supersonic aircraft, where aerodynamic efficiency at speed is the primary design requirement. A sharp pointed profile reduces wave drag by allowing the aircraft to pierce the air with minimal disturbance, delaying the formation of shock waves that generate significant resistance as the aircraft approaches and exceeds the speed of sound. Fighter aircraft such as the F-16 Fighting Falcon and the Eurofighter Typhoon use slender conical noses, as does Concorde in its raised cruise position. The interior typically houses fire control radar, infrared sensors, or targeting equipment behind a pointed radome shaped to match the fuselage profile. The trade-off is reduced internal volume compared to a rounded nose, which limits the size of systems that can be packaged inside. Droop nose. The droop nose is a movable design developed specifically to solve a contradiction in supersonic passenger aircraft. At cruise speed, a supersonic aircraft needs a long, sharp nose to minimize wave drag. At low speed, during takeoff and landing, that same nose blocks the pilot's forward view of the runway entirely. The solution on both Concorde and the Tupolev Tu-144 was a nose section hydraulically lowered during takeoff and landing to restore visibility, then raised back to its streamlined position for cruise. On Concorde, a separate visor covering the windscreen could also be lowered independently from the nose, giving crews different combinations for different phases of flight. The mechanism added weight and complexity, but was considered essential given the extremely high approach speeds both aircraft operated at. Visor nose. The visor nose, sometimes called the swing nose or upward hinged nose, is a loading configuration on dedicated freighter aircraft where the entire nose section hinges upward to allow straight-through loading of cargo into the forward fuselage. The Boeing 747F, Antonov AN-124, and Lockheed C-5 Galaxy all use this arrangement. By opening the full cross-section of the fuselage at the nose, oversized items such as vehicles, military equipment, and industrial machinery can be loaded without the constraints of side doors alone. The engineering challenge is significant. The nose must carry full aerodynamic and pressurization loads in flight, while also functioning as a door capable of thousands of open and close cycles. On the Antonov AN-124, the visor nose works in combination with a rear loading ramp, allowing vehicles to be driven in at one end and out the other. Ogival and area-ruled nose. The ogival nose is a geometric profile derived from the ogive curve, producing a smooth tapering pointed shape that transitions efficiently from the narrow tip to the full diameter of the fuselage. It is used on supersonic and transonic military aircraft, missiles, and rockets, where the nose must manage that transition with minimum wave drag. The F-22 Raptor, B-1 Lancer, and most air-launched missiles use ogival profiles. Area ruling, a related aerodynamic concept developed by Richard Whitcomb at NACA in 1952, addresses how cross-sectional area is distributed along the aircraft's full length. An aircraft designed to the area rule narrows at the wing roots to compensate for the cross-section added by the wings, producing the wasted fuselage visible on the F-102 Delta Dagger and the Convair B-58 Hustler. Applied correctly, area ruling reduces transonic wave drag by up to 50%.